Hello, math students. Topic 12 is Introduction to Second-Order ODEs, which are ordinary differential equations. A second-order ODE involves at most the second derivative of a function of one variable. In some cases, the second derivative can be isolated as below, which is called normal form. So you get the second derivative alone on one side, and on the other side should only be a function or expression involving the independent variable t, the dependent variable y, and then the first derivative of the dependent variable. Now these letters, of course, could be anything. You could have w be your dependent variable and x be your independent variable, so don't get caught up on y's and t's only. Continuing, a second-order ODE is linear if it can be expressed in the non-normal form below. So for a linear second-order ODE, you do have the second derivative isolated, or I should say, not necessarily isolated on one side of the equation, but you have a coefficient of 1. So it's just y double prime plus, and then some sort of function of the independent variable times y prime plus some sort of function of the independent variable times y equals some sort of function of the independent variable. This is called a linear second-order ODE. Now, what would make it nonlinear would be if this form wasn't possible, which could happen when you have something like if you put a square on that y, then this would be nonlinear. So the powers on these derivatives on the y and its derivatives have to be 1. So there's an implied first power on that second derivative, implied first power on that first derivative, and implied first power on the dependent variable. If you put a square root on the second derivative, this would be nonlinear because square root is a 1/2 power. If you multiply y times y double prime, then this cannot be put into the form that we have listed here. So that would be nonlinear. If you put a y prime over a y like this would be a nonlinear term. So you have to pay very close attention to the dependent variable and its first and second derivatives. They have to be in separate terms, raised to the first power, potential coefficient function of t in front of the y and y prime, and then a potential function of t over here on the right side of the differential equation, but a 1 coefficient in front of the y double prime. Okay, more terminology that we'll be using later in this course. This g of t function. If that's equal to 0, then we say that this ODE is homogeneous. Otherwise, we'll say the ODE is inhomogeneous. So let's practice some of these terms. Determine whether the second-order ODEs below are linear, and if so, whether they are homogeneous. Being mindful of which variable is the independent variable and which variable is the dependent variable. Okay, so looking at the first one, the dead giveaway of which variable is dependent is the one that has the derivatives on it, so the y. So t, therefore, is the independent variable. And to determine if this is a linear differential equation, we're simply going to try to put it into this form that we see right here. So I'm going to prep by getting the y double prime term to lead off. If there's a y prime term, move it over to join, so minus 4y prime. Notice there's no y term. That's fine. We could have this function q of t could be 0, meaning that this term isn't present, and that would still be linear, right? So it's okay that these functions here could be 0. And then we leave that negative square root of t on the other side. The next step would be we want to get the coefficient of y double prime. That looks like a y to the 4th. Let me make sure that looks like a y double prime. We want the coefficient of y double prime to be 1. So we want to divide everything by t squared next. So we have t double prime minus 4 over t squared times y prime is equal to negative radical t over t squared. And now we have the desired form. Notice that the y double prime is isolated. We have a y prime raised to the 1, and with some sort of function of the independent variable in front of it as a coefficient. We don't have a y term, but that just means the q of t was 0 in this case, so that's gone. And then we have a g of t function over here. And it's not 0 because there's something there. Therefore, this is linear, and inhomogeneous. I'll just abbreviate it. Let's look at the next one. The dependent variable is z because that has the derivatives. So we're going to assume that the x that I see here is the independent variable. Z is dependent, x is independent. So again, let's get the z double prime, and I cross my z's when I handwrite them. I suggest you do the same, otherwise they start to look like 2's, which is bad. Let's minus the 4z prime over, and then add the square root of z, and then that leaves a 0 on this side. And next thing I would do is divide everything by x squared to get z double prime isolated. I'll put a 1 over x squared in front of this z, square root of z, and dividing 0 by x squared just stays 0. So it looks pretty close to being the correct form. We have the second derivative alone, then we have a function of the independent variable times z prime, so that looks exactly like that. Then we have another function of the independent variable times, oh, here's the problem. We have radical z. This dependent variable here has to have a 1 exponent, right? And this z down here has a 1/2 exponent. So we have a nonlinear term. We'll just say that this here is the nonlinear term. This is the reason why we're having a nonlinear equation. And if it's not linear, then we don't bother describing whether it's homogeneous or inhomogeneous as far as this exercise here is concerned. Let's move that over slightly. Okay, now let's shift gears to the next one. This time, the little curveball is thrown at us. The x's have the derivative, so x is the dependent variable and t is the independent variable. So again, I'm going to get the x double prime term, far left side. I'm going to subtract this 4x prime, and then add this x radical t. And that leaves a 0. And I'm going to switch this around just so it matches like this form. So I'm going to put the dependent or independent function in front of the dependent variable. So to do that, I would simply just switch the order of these two things. You don't have to do this, of course, but just make sure that this x is not inside the radical. Or maybe put a dot right there. Then I'm going to divide everything by t squared. So we have x double prime minus 4 over t squared times x prime plus radical t over t squared times x is equal to 0. Now the dependent variable and its derivatives all are raised to the first. So that's all good. A 1 in front of the x double prime, some sort of function of the independent variable in front of x prime, and some sort of function of the independent variable in front of x. And then we have a 0 on this side in this case. So this one is linear, and it's also homogeneous. Spell that right. Homogeneous. Okay. Next idea to be aware of. Two functions are said to be linearly independent on an interval from a to b if neither function is a constant multiple of the other on that interval. Determine whether each pair of functions form a linearly independent set. Okay, so this is this pair. If it's possible to multiply one of these functions by a constant to turn it into the other function, then we say that they are not linearly independent. And in this case, you can certainly see that if you were to take the function u and multiply it by half, and then so negative 5 halves times u would equal the v function. I'll leave that to verify. If you do negative 5 halves and multiply it by 2, you're going to get negative 5t sine of 3t, which is what the v function is. Or you can see that the v function is going to be negative 2/5 of the u function. Right, take the v function and multiply it by negative 2/5, and you'll get the u function. So in this case here, we say that they're not linearly independent. I'll just abbreviate. That's not abbreviation there, but so not linearly independent because one can be multiplied to become the other. Now, using technology to help understand this, I'm going to go ahead and plot these two functions. And here's what they look like. This is the u and v function. And if it's when you do a multiple of one function, it's like doing vertical stretches of it. So I'm going to put an a in front of one of these. It doesn't matter which one I put it in front of. I'll put it here, negative 5a, and then I have a slider for a. Currently a is at 1. But if I vary a, I'm just doing different multiples of the blue function, and you get different vertical stretches. The question is, can I do a vertical stretch of one function and make it match the other? And the answer in this case is yes. It's going to be at negative 0.4. Right? If you multiply the blue function by negative 0.4, which is negative 2/5, you'll get the red function, which is here, that's like saying multiply v, multiply the v function. I have a typo here. I don't know, that was a mistake. U is equal to negative 2/5 times v. So if you multiply the v function by negative 2/5, you'll get the u function. Sometimes it's obvious that when you graph two functions that you cannot multiply or vertically stretch one to make it look like the other. And if that's obvious from the imagery, then you know that the two functions are not linearly independent. Hope I said that right. If it's obvious that one function cannot be scaled to equal another, then the two functions are linearly independent. That sounded correct. Okay, here's two new functions, f of t and g of t. F of t is sine 3t, and g of t is a constant, or sorry, t times sine 3t. Let's graph these on Desmos. Let me open up Desmos. Let me hide those graphs. I'm going to park a back at 1. I've already typed in all of these functions, and I have an a on one of them. So here's the two functions in question now, sine 3x and x times sine 3x. And then I have an a in front of the x sine 3x because I'm about to scale it. But you'll notice that it's impossible to scale the blue to make the red. And if you look at various scale factors of the blue, there's no way we're going to get the red out of this. Because one thing that's always true for the amplitudes of the blue wave is that they have varying amplitudes, but the red has a constant amplitude. And so there's just no way that we can multiply the blue by a constant and turn it into the red. So we would say something like this. F is not some sort of multiple of g, and g is not some sort of multiple of f, right? There's just no way. Maybe I'll put a different constant here. They don't have to be the same. They're not going to be the same constant. If, like over here, for example, if the constant that you would multiply u by to get v is not the same constant you would multiply v by to get u. And in fact, they're reciprocals of each other. So maybe I could say 1 over a here. But there's no way you can scale either one of these to make the other. So these are, I'll just put Li for linearly independent. Circle some answers. Let's go to the next set. W of t and z of t equals 2 cosine 3t and negative 5 cosine 2t. Now these two cosine waves have different periods. That's going to be a problem. You won't be able to get them to match up if they have different periods by doing vertical stretching. Let's just verify that. And they have different periods because one's a 3t, one was a 2t. Let me put a back at 1 and then reveal these two graphs. So they have different periods. Period is how long it takes to repeat itself, and amplitude is how far up and down it goes. But they have different periods, and if I do any sort of stretching of the blue wave, there's no way I can ever get to the red wave. That's just going to be a given because they have different periods. It just can't happen. So we would say in this one here, there is no constant that you can multiply z by to turn it into w, and vice versa. That means you can't turn w into z by multiplying by some sort of constant. It's not going to happen. So these are linearly independent as well. All right, this one's a little bit trickier. We have sine t times cosine t and then negative 5 sine 2t. Let's see graphically whether we can see linear independence. Let me hide these and put a back at 1. There we go. And reveal the last two functions. the blue and the red, notice they have the same x-intercepts and they have consistent amplitudes. It does make it feel like therefore I could do a vertical stretch of blue to make it into red. And if I just toy with this vertical stretches, oh yeah, so it's possible to make these two things be the same. Looks like negative 0.1 might be the choice of A. To multiply the blue function by negative 0.1 might turn it into the red function here. And the reason this is, you might want to remember, or you might want to recall that we have a trig identity that can be used here, sine of 2t. So this n function can be rewritten. If you recall, sine of 2t is 2 sine t cosine t. In other words, n of t is just negative 10 times sine t of cosine t. Sine t times cosine t, which is just negative 10 times the m function. So if you take the m function and multiply it by negative 10, you'll get the n function. That suggests that if you take the n function and multiply it by negative 1/10, you'll get the m function. So these ones are not linearly independent. Okay, let's go to the next slide. Use your knowledge of functions and their derivatives to find as many non-constant functions that satisfy the following ODEs. I wrote y of t here, but not all of these deal with y, so probably best just to not put that there. In particular, find a linearly independent pair of solutions to each ODE. Okay, so we're just going to say these are very basic second-ordered partial differential equations, y double prime equals y. We're trying to find a function that when you differentiate it twice, it's the same thing as what you started with. Now, the obvious answer to this one is e to the t. We'll use t as our independent variable for all of these. Y equals e to the t. It's certainly true that if you differentiate this twice, you will get e to the t still, and therefore this differential equation is true. Another option here, now I'll give you a moment to think about this. You might want to pause the video and try to come up with a second one. And then replay, if you're ready now, e to the negative t. Because when you differentiate e to the negative t, let me put subscripts on these y's, by the way, so we can view them as separate things. So if I differentiate y sub 2, I get negative e to the negative t, but when I do a second derivative, it's going to go back to positive. In other words, we get right back to the original. Y sub 2 double prime is equal to y sub 2. So here we have two different, we have e to the t and e to the negative t. And the question is, are they linearly independent? If I graph e raised to the x, let me just copy that, and do e to the negative x. There we go. Hide these sine waves, I don't want to see those. So here's two functions. It's not possible to scale one into the other. All right, let me put an a in front of this one here, and then toy with different values of a, and there's no way I can turn one function into the other. So when you have e to a kx and you have e to a different power of x, or e raised to a different multiple of x, then we have linearly independent. So these are linearly independent. Other solutions, though, it turns out that if another possible answer here is the hyperbolic sine. If you recall, when you differentiate hyperbolic sine, you get hyperbolic cosine. And when you differentiate hyperbolic cosine, you go back to hyperbolic sine. So the second derivative of hyperbolic sine is back to hyperbolic sine. That's also true, though, for hyperbolic cosine. So here's another possible answer. And we just wanted to find any pair of these that are linearly independent. So let's go with this pair right here. We've already verified that that's linearly independent. But you can also show that this pair here is linearly independent. In fact, you could show that any pairing, this pair is also linearly independent. That can be shown to be true. So pretty much any pair from the four of these could be used to form a linearly independent set of solutions. The next one, z double prime equals negative 9z. All right, so a second derivative is going to produce a negative 9. Well, let's see. If z was e to the 3t, let's see what would happen here. Z prime would be 3e to the 3t, and z double prime would be 9e to the 3t, which is equal to 9 times the original. Oh, so that's close, but it's not negative 9 times the original. So that's not going to cut it. We could use some imaginary numbers here because like 3i, because 3i times 3i would be negative 9, but let's not go there for right now. Let's try to stay in the real numbers, although we will go to the imaginary numbers soon in this class. Let's try to think of another function that when you differentiate it, you get the opposite of the original. Oh, the trig functions. Like what if z is equal to sine of t, for example? The derivative of sine is cosine, and the derivative of cosine is negative sine. So it gets back to sine, but it's the opposite. But now we got to get that 9 in place. If I put a 3t there, let's test this. Let me put a subscript on here. This is going to be one of our answers. z1 equals sine 3t. Let's just test it. z1 prime is equal to 3 cosine 3t using chain rule. And z1 double prime, one more derivative, will be derivative of cosine is negative sine, and there's already 3, and chain rule gives you another 3, so negative 9 sine 3t, which is negative 9 times the original. So this works. So we found one. A second one, z sub 2 solution is going to be the cosine function of 3t. And the sine and cosine functions, because they are phase shifts of each other, there's going to be no way that you can scale one into the other by multiplying by a constant. So these do form a linearly independent set. Let's just keep moving on. U double prime equals 5u. This time no negative it looks a lot like this one here, except there's no negative here. So I think our exponential helped us with this one. So if I say u is equal to e to the, if I put a 5t there, then u prime will be 5e to the 5t. And u double prime will be 25e to the 5t. That's not what I want. I want u double prime to be 5 times the original. This is u double prime is 25 times the original. So I want this to be a 5 after you do 2 derivatives. So I want the constant, the coefficient of the t there to be a radical 5. So if that's a radical 5, now let's test it. U prime is radical 5 e to the radical 5t, and then u double prime multiplied by another radical 5 will give us the 5 that we desire. And this is 5 times the original, so this works. So this is one possible answer. We'll call it u sub 1. Another one is if this was a negative radical 5, this one will work as well, because the first derivative will have a negative radical 5 coefficient, but the second derivative will go back to a positive 5 coefficient. So here's 2, and these are also linearly independent. In general, with second-order differential equations that are linear, we're going to be able to find 2 linearly independent solutions. They don't have to be the same pairing. Like we saw, we had options over here, but you should be able to find 2 linearly independent solutions to these second-order linear differential equations. And these are linear, by the way. I'll leave that to you to verify. Next slide. Suppose that y1 and y2 are linearly independent solutions of a linear homogeneous second-order ODE. Then the general solution is as given below. So here's our second-order linear homogeneous ODE. It's linear because it has the linear structure. Second order because there's a second derivative. Homogeneous because there's a 0 on this side. And if y1 and y2 are linearly independent solutions to it, then we can form a general solution by combining them with arbitrary constants. So the general solution will be c1 times y1 plus c2 times y2. And then to find a particular solution, you just got to figure out what c1 and c2 are so that the given conditions are satisfied. So we're going to practice that right now. Find the particular solution to the differential equation below with initial conditions. So this is y double prime equals y. This is back to that, we did that one right here. We already found, we're going to use those 2 linearly independent solutions. So let's write it this way. So 2 linearly independent solutions are y1 is equal to e to the t, and y2 is equal to e to the negative t. So the general solution can be formed from these by saying our solution will be y is equal to some constant c1 times e to the t plus some constant times e to the negative t. We do c1 times y1 plus c2 times y2. Now we want to find the particular solution. Now, in order to find a particular solution, we need to have data not only for the y at a certain t, but also for y prime. We need to have, if you're working with a second order differential equation and you want to be able to find a particular solution, you need to have double information. You need to know information about y and y prime. In fact, every derivative of y below the degree of the equation. So this is a second order equation. So we got to have a zeroth order information and a first order information. If this was a third degree, then I would want to know up to y double prime in order to get a particular solution to a third degree. But this is just on second order. This whole unit is on second order, so that's what we're focusing on. Okay, let's see. Back to our... Okay, so we want to satisfy this statement and satisfy this statement both. So I need to do a derivative of this so I could get this one here set up. So let's go ahead and find the derivative of our general solution. The derivative of c1 e to the t, well, that's just going to be itself. That's not going to change. But the derivative of the next one, the derivative of e to the negative t, will produce a negative. So we'll have minus c2 e to the negative t. Okay, let me move this over slightly. And now what we're going to do is we're going to take this pair of equations, the general solution and its derivative, and plug in 0 for t, and then negative 5 for y, and then 3 for y prime. So we're just going to plug in this information. Let's do this top one first with this first equation. So negative 5 goes in for y at the same time that 0 goes in for the t's. And then we're going to use this y prime equation to plug in 0 for t's and change y prime to 3. Now these e to the zeros all go away. They all become, let me move this down here, they all become 1s. And so our system now looks like negative 5 equals c1 plus c2. And the other is 3 equals c1 minus c2. And we want to solve this system of equations for c1 and c2. And you can use substitution, elimination, matrix methods. There's a lot of different ways you can solve these systems of equations. This one here looks like elimination is going to be really easy. Just add the two equations together because notice the c2's will cancel each other. So when I add negative 5 and 3, I get negative 2, and I get 2c1. And then the c2's cancel. Therefore, negative 1 is equal to c1. And once you know that c1 is negative 1, you can plug it in either here or here. Doesn't matter, right? Both spots, and then solve for c2. Let's plug it into the first equation. So we have negative 5 is equal to negative 1 plus c2. Add 1 to both sides, so negative 4 is equal to c2. And now I'm ready to write down our particular solution. Particular solution is y is equal to, and c1, so I'm just rewriting the general solution right here, but with the correct c1 and c2 in place. So c1 is negative 1, so we have negative e to the t, and then c2 is negative 4, so minus 4 e to the negative t. Now I'm going to leave it to you to verify using technology. You can type this information into, say, Wolfram. You say solve y double prime equals y, comma, y of 0 equals negative 5, comma, y prime of 0 equals 3, and it'll give you this result here as the particular solution. If you do two derivatives of this, you will see that you get the original back. And it's also true that if you plug 0 in for t right now, you're going to get negative 5 back. And if you do the first derivative of this answer and then plug in 0, you'll get 3 back. So it will satisfy all the conditions of our differential equation. And again, I leave that to you to verify those things. Okay, and our last slide for this introduction lecture. Perhaps you did not realize it, but we have already discussed a situation that involves second-order ODEs. Reconsider the situation below. An object has a mass of 5 kilograms and is dropped from rest at a height of 200 meters. The force due to air resistance is proportional to the velocity of the object and is 20 newtons when the speed is 10 meters per second. Okay, so this is a flash or a trip down memory lane, if you will, when we did applications involving objects falling through the air, where there's air resistance. First thing you want to do is figure out, well, we know the total force acting on an object is going to be the force due to gravity and then plus the force due to the air resistance, right? This was our setup, how we did this. We want to figure out what the force due to air resistance is. So let me move this over here and first determine what this force due to air resistance is. Now we're told that the force due to air resistance is proportional to the velocity. So it's equal to some constant times the velocity. And also the force due to air resistance is always the opposite direction of the velocity. So velocity is positive. Remember, positive velocities we'll say is up and negative velocities we'll say is down. So if the velocity is positive, if v is positive, you want the force due to air resistance to be pushing down, right? When the object is going up, the resistance from the air is applying a force that's pushing the object back down. So we want a negative kV is a good setup for this. The force due to air resistance is 20 newtons at the same time that the velocity is 10. And so the velocity is 10. So we can solve for k, and we get k is equal to negative 2. Oh, I should also say, you have to be careful here. The force due to air resistance, if the velocity is 10, then the force should have been negative 20 because it should be in the opposite direction. The k should be 2. Right, very tricky. Always be mindful which way your forces are being applied and which way your velocities are. So we're assuming that if the object's going up, so velocity is positive 10, then there should be a negative 20 force associated with that. K should be 2. So let's go back to our total force. And total force is mass times acceleration, Newton's law. The force of gravity is always down, so it's always negative force, and it's mass times the acceleration constant. And then we just found out the Fr is negative kV, where k is 2. So minus 2v. Now, when the object is going up, all the forces acting on it are down. Right? So when v is positive, g is a constant, remember. So this is always a negative number here because mass is positive and g is a positive constant. So this is always a negative component. But v changes from positive to negative depending whether the object's going up and down. If the object is going up, then the air resistance, so v will be positive, and this will wind up being a negative contribution to this already negative force. So we have a double negative because both forces are trying to pull the object down, gravity and the air resistance. But when the object turns around and starts to fall back down, v will switch to negative, which means this part here switches to positive. So we have an offsetting force. We have the object is falling down, so gravity's still trying to pull it down, but you have an air resistance that's trying to push it back up. So just making sure our signs all look good here. Both should be minus and minus. Then the next thing we did is we rewrote A as v prime and divided everything by m. So we wound up with this differential equation that we had to solve. And this is a first order. But keep in mind that velocity is the derivative of position. So we could change this to s double prime, where s is the position function, negative g minus 2 over m times, and v would be s prime. And just like that, we really had a second order differential equation we were working with. However, we were able to treat it like a first order and solve that to get the v function. And then once I knew the v function, I could then anti-differentiate and get the s function. That's what we did in our homework. But in general, there's a special case of a second order differential equation. In general, differential equations, if you can isolate the y double prime, would be some sort of function of t, y, and y prime. But the special case is that if the second derivative could be expressed as a function of just t and y prime, there's no y here. If that's the case, then you could do a switch of variable and let u be equal to y prime. Therefore, u prime is equal to y double prime, and you can rewrite this second order differential equation as a first order. Y prime equals a function of t and u. And now you can just use what we did from the first unit and solve this differential equation. It's a first order differential equation. Get a solution u, but then remember that u is equal to y prime, and then you would find y by anti-differentiating, or you would find you would find y by anti-differentiating u. Okay, and that concludes our introduction lecture on second order ODEs.